about weight and mass, and it's very easy for people to get confused, but if you remember that weight is really the same thing as the force of gravity on objects here on Earth, and mass is the amount of matter, keep in mind that force is a key word here. Force is measured in newtons, and it is a vector. It's a force of gravity, so it points down towards the center of the Earth. Matter, for example, is measured in kilograms. And so imagine you take yourself, this is you, standing here on the Earth. You could measure that force of gravity on you. You could measure the amount of matter, and you'd have the number of newtons and the number of kilograms. And then transplant yourself instead to the moon. And the moon is a less dense object than the Earth, and it's a much smaller object. So the amount of matter stays the same. On the moon. But the force of gravity is less because you're on a less massive object, so your weight decreases. Now here on Earth we have a pretty easy conversion from weight, which is the force of gravity, F sub g, to matter, mass. And that is F sub g, your force of gravity, equals the amount of mass times g, where g is a constant. It means the magnitude of the acceleration due to gravity here on Earth. And g is this kind of magical number that we'll see, 9.8 meters per second squared. So if you want to convert from mass in kilograms to weight in newtons, you just got to use F sub g equals mg. It looks a lot like Newton's first law, or Newton's second law, and there are reasons for it, but it's not the same. G is not an acceleration. You can be standing here on Earth, you're not going to be accelerating, but your weight is still going to be your mass times 9.8 meters per second squared. So, for example, if you are around 50 kilograms, which is kind of what your average student might be, 50 kilograms times 9.8 meters per second squared, here on Earth, you're going to weigh a slightly less than 500. I think it should be, I don't need the calculator for this, 490 newtons. You can work backwards too to go from newtons to kilograms pretty darn easily. On other planets, however, g is not 9.8 meters per second squared, and you can actually figure out what it is. This is the equation you'll see on your reference table. You don't actually see this in the form here, but it is equal to F sub g divided by m. So you could measure your weight on the moon, and you could know your mass on the moon and find g, which is not going to be 9.8 meters per second squared. It's probably going to be closer to about, just a guess, 2 or 3 meters per second squared on the moon. So how do you know whether, when you see an object, whether you know its mass or its weight? And sometimes whether you need to find the other one or not. Well, I'm going to draw a free body diagram of an object here. And you often see things described as like a 20 Newton block. I love talking about blocks, right? 20 Newton block. So that's almost like an adjective being used to describe this block. We have to ask ourselves, what does it mean? Well, newtons is a force, right? So this 20 Newton block has clearly got a force of gravity of 20 newtons. So if we draw this as a free body diagram, we could say the weight, F sub g, is equal to 20 newtons. That can give us a lot of other information sometimes too. Like if it's on a flat surface, we'll know that it's got to be balanced. So your normal force will be 20 newtons also. And this can be useful when we're figuring out things like frictional forces, for example. So we're going to definitely see more of this as we go on in other units regarding weight. But just remember, when you see something described as like newtons, that's usually the weight. It's not an applied force. You might apply 10 newtons of force to it. Maybe you see 20 Newton block going right at a constant speed. Whenever you see these words constant speed, you should alarm bells should go off. And you might want to find the frictional force. What we find is the frictional force actually depends on the normal force a little bit, but we don't need to, there's equations, we don't even need to know them because constant speed tells you things are balanced. So if there's 10 newtons here, there's got to be 10 newtons there. You don't even need to know the normal force to answer this one. So that has been my introduction into the difference between weight and mass. Thank you.